You have a little reminder up here about how to go from log to exponential, and it also works the other way, going from exponential to log. And then as a reminder, if you have a natural log, that's a log with a base of e. And if you have a common log, you see no log down or no base down here. That's a base of 10. So that's your common log. Example 1 says find the inverse of f of x equals 2 to the x graphically and algebraically. So let's kind of discover what a log graph looks like here. We have already graphed x or 2 to the x power. If you go back to lesson 3, we already did this graph. So I just recopied this table. And so we should get this graph here. And as a reminder, you can just punch that in 2 to the x. There's your graph. And then go to table to get some values here to plot, right? But we've already done this, so I'm not going to spend a lot of time on that. So those values are already here. So let's graph these. Okay, and we have a horizontal asymptote. Similar here. We have a horizontal asymptote. And I'm going to do it over here at y equals 0. So when we plot those ordered pairs, we will not cross that x-axis there. Okay, so there's our graph. If that didn't make sense, go back to lesson 3, please. So the domain is negative infinity to infinity, goes from arrow to arrow, or all exponentials have a domain of all real numbers. The range, as we go from the bottom to the top, the first thing we encounter is that asymptote at 0, so it's not included. And then it's going to keep going up forever to infinity. And then I already put that information on my graph here. My asymptote is at, let's go ahead and put horizontal asymptote at y equals 0. Okay, so all of that should be a review. So now let's go over here to the inverse. So we learned in lesson 2 how to find the inverse, and you take these ordered pairs and you switch that x and y. So I'm going to take this x column and I'm going to rewrite it over here as my y column. And then I'm going to do the same thing and write my y column over here as my x column. Okay, I'm going to plot those. I'm not going to connect them yet until I talk about these points. Okay, and they kind of behave similarly, right? That as these x values are getting smaller, these are going to get smaller as well. And so they're going to get closer and closer. This one has a vertical asymptote at x equals 0. We have a vertical asymptote at x equals 0. So when we connect our red lines, we are not going to cross that x-axis. Now we need to label our graph since we have multiple graphs on the same graph. This is my inverse function, and I should have labeled this one as my function. And there's a special relationship between our inverse functions. And that is that they are symmetric along the line of y equals x. So when we put that dotted line in there, we can see more visually how they are symmetric. So of this inverse function, what is my domain? You can do this one or two of two ways. As you go from left to right, the first thing that we encounter is this vertical asymptote at 0. And then it's going to keep going forever to infinity. Well, that's the same as my range right here, which we've already found out that the domain and range switch places when we're talking about the function and its inverse. Following that same logic, my range is then going to be negative infinity to it. Oops, let me put that in red. Ooh, ugly now, I hate that. All right. Negative infinity to infinity. Okay, because again, that domain and range switch places. But also, if you look at that graph, as you go from the bottom to the top, we have an arrow to an arrow. Now we can see that these are increasing. They're just increasing very slowly in comparison to my x, very rapidly here, and then it starts leveling off some. Okay, so we have found this inverse graphically, but now what do I name this inverse function? So let's find it. To find it, we take our function and we follow our steps to find inverses. Okay, let me look back in my notes real quick. Here's our steps to find an inverse function. So the first thing we need to do is replace our f of x with y. So now this is y equals 2 to the x. Now I need to interchange my x and my y. So we get x equals 2 to the y power. Step 3 is to solve for y. We went over last lesson, maybe 2 ago, that we cannot solve for a variable when it is in the exponent position. What we have to do is rewrite it. So I'm going to take my exponential and rewrite it into an equivalent log. So to do this, we go base to the other side of the equals. So this is log base 2 of x, and that equals what's left, my exponent of y. So now lastly, replace y with your inverse notation. My inverse is log base 2 of x. So there is my connection there. The reason we are doing inverses and exponentials and logs is because exponentials and logs are inverse functions of each other. Now, let's kind of look at what happens when I change my base of a log to something other than 2, because this is what my log looks like when it is log base 2. But what happens when I have something else? So here's what we just graphed. Here's my exponential with 2 to the x. Here is my log here in green, log base 2 of x. And then that line of symmetry, y equals x. So I'm going to take away these two. When I have log base 3 of x, you can see here, it is going to kind of level out faster. Log base 4 is going to level out even quicker, and log base 5 quicker than that. Now, just like with exponentials, we have some things in common here. First thing, they all have an x-intercept at 1, 0. So unless we shift this up, down, left, and right, they all have that same x-intercept right here. I don't know if I said y-intercept earlier, but the same x-intercept at 1, 0. They also all have the same vertical asymptote at x equals 0. So, coming back over here, our graphs are going to look like this right here when we have a base that is greater than 1. You can't see what I'm writing, but when we have a base that is greater than 1, we have this shape of an exponential where that is always increasing.